So again, question of the day, does the distance to the sun determine the seasons? We're going to explain that. So if you wouldn't mind, Sam, turning it over this way, and I'll give us a sentence starter. The distance to the sun, blank, the seasons in Iowa. Oops, I should say cause the seasons in Iowa. So the distance to the sun does or does not cause the seasons in Iowa. So that's going to be where we start. I'll move this out of the way so everybody can see. Jose, do you have a pass?
No.
Then don't be late. And get those things out of your ear. And get your notebook out. And all those things. And Zai, don't throw things, honey. Just hand them. Good, no. All right, so I'm going to go ahead and be quiet and take attendance. I will put 1 minute on the clock. I need you to get out your lab from yesterday. Sam, could you turn it back over here? Get your lab out from yesterday so that we can have it help us answer this question. 25 minutes seems a little bit long. Let's go a minute. And I'll take attendance. Write down the sample starter.
She just gave me her last piece, so it's not gonna work.
Could you not? Just leave her alone for a minute, don't jeopardize her success, and then as soon as we're done, you can ask her whatever you want. But I don't think she has any. All right, got 4, 3, 2, 1, and we are done. Before I do this, can I ask how many of you are going to be gone on the Disney trip? Okay, so if you're on the Disney trip, I've got a packet of information. One of them we are starting today. I just weren't you absent. Do you have a pass?
No, sorry.
You do?
No.
Okay, everybody put their hand down, and I don't have that kind of memory, but I can just remember everybody that's going to be gone. All right, did I get everybody? Fabulous, thank you.
No.
All right,
Sarah's going to Disney World.
let's go ahead and talk about this. Turn with your parashare partners. I'll go ahead and give you a 15-second countdown, Jared, and your time starts now. Go.
I think it does.
Well,
No, I don't think it does. I don't think so.
You're welcome.
closer to the sun during the day.
Yeah, so I don't. Did we do anything for Spanish? No, I think we just played a Quizlet and then did like.
All right, here's our time. 3, 2, 1, and we are done. What do we think? Does the distance to the sun cause the seasons in Iowa or does not cause the season in Iowa? Sam, turn this way, please. What do we got? Somebody raise your hand. Be a warrior. Jaren.
It does not.
Does not. How many of you agree with Jaren? Yeah, me too. Does not cause the seasons in Iowa. And it says explain. Well, one thing we could do is explaining as justification for knowing it does not. If it was summertime in Iowa because we're closer to the sun, wouldn't it also be summertime in Australia? If we were closer to our sun, and that was the reason it would, right? If we're closer to the sun where it's going to warm us up, that means it's going to warm up the whole globe. But that's not what happens. When it's summertime in Iowa, it's wintertime in Australia. So that's not what's going on, right? That's not what's happening. And also, what's another piece of evidence that we could use to explain? We're actually closer to the sun when?
During the winter.
During the winter time, in January. We're actually closer to the sun in our orbital path around the sun when it's the middle of January. What? Let's go ahead and look at our data to support this. Could you please get out your lab from yesterday and let's go ahead and look at the lab from yesterday. I am going to go ahead and pull up a PowerPoint that I have created over this lab. I don't like that it is showing like this, but it is what it is. All right, so we're gonna talk about what causes our seasons of winter, spring, summer, and fall. So get out your lab. I'm not going over word for word on our lab. I'm going over the big ideas on each part so that we can kind of fill in the blanks and help ourselves through it. So the first part of what causes seasons, or our seasons lab, was part 1. And part 1 was all about the distance from the earth to the sun. So seasons are not caused by the Earth's distance to the sun. We are actually closer in distance to the sun during when? Winter. So if we are looking at, and I'm really hoping that this works. Okay, good. If we're looking at, this is our seasons lab, can someone please tell me these times? So in January, what was the distance or the diameter? We first looked at a picture of the sun and we measured its diameter from one side to the other at 2 times. One was January. What was the diameter in January? Yep. 18.3. And I know some of you are like, no, it's 0.5, whatever. What about our distance in July? The distance from side to side of the sun? Yeah. 17.7. All right. So then, given that we know the sun has a constant diameter, meaning from side to side, that means the sun doesn't go like this. It doesn't do that. What then is the only reasonable explanation for the sun's apparent size in the picture? What's the only reasonable explanation? Billy? As we orbit around the sun, what? Okay, so what's the, okay, so you're saying that we're changing in our distance from the sun? Okay, so as we orbit around sun in an ellipse, our distance from the sun changes. Is that basically what you're saying, Billy? Okay. According to this measurement, then, are we closer to the sun in January or July? January, yeah. January. How do we know? Because we're bigger, right? The sun's bigger to us. Like if I am here and then I come closer to Claire, what happens to my size? I get bigger, right? So does this information support the idea that seasons are caused by Earth's distance to the sun? No, and then explain why, right? Because if it was, we would have, right, we would be closer in July when it's warmer on the planet, not in January when it's colder. It's just silly, Ethan. That's just silly talk. It's just really silly. All right, so then the next part is the tipping Earth. And we're going to go ahead and go through that in just a moment. All right. So then seasons are not caused by the Earth's distance to the sun. We're actually closer in distance. Let me go back to this. Okay, we are actually closer to the sun during our winter. And here's a picture of that. During January, right here, when we have our winter and Australia is having its summer, we're actually 147,000 kilometers to the sun. This is called perihelion. This is when we are closest. Aphelion, which is A for away, we're actually farther away from our sun during July 4th, about 152 million kilometers. Do you know that we're coming up to the equinox? Do you know what equinox is?
No. Oh, is that when the sun, moon, mix?
No. That's eclipse.
Oh, mix.
Yes. Equinox is when we have, how many hours are in a day?
24.
There you go. So in the winter time, it's really depressing for Mrs. McGrain because during that 24-hour period, we have less daylight hours. We might have 6 daylight hours, and then we've got like the rest are all dark, right, nighttime. Yeah. Equinox means equal day and night. We've got 12 hours of day and 12 hours of night.
Really?
So we've got, 12 hours of daylight and 12 hours of nighttime. And then after that moment, we're getting closer and closer to that moment, Well, this was for 2120
What if
or
it was
2021.
23 hours?
We're getting closer to that, and then what happens is then it switches, right? And we get longer daylight hours and less nighttime hours. Yeah, yeah.
I'm not.
Where it's like
Asking a
9:30 and it's
question.
still light out.
And then at 6 a.m.
All right. The facts. We're going to now look at the next part. This is part 2 on your lab. The Earth does not wobble or tip back and forth on its axis. I think one of our friends, Miguel, in our pre-assessment said this. During the early orbit, it is at a fixed tilt. Can anybody remind me from the lab, what is the fixed tilt?
So when the axis is like
What is the actual angle, though?
9.
Go ahead, Samuel. 23.5. So it is tilted at 23.5 degrees, and it's pointed directly at Polaris, which is the North Star. Which is why during our lab, I said, hey, the North Star's up there, point that little axis to the North Star. So for me, if I had this, it would be like this, right? My axis is pointed, it's tilted towards that direction. And then if this was the sun, right? Wow! If this was the sun, then this thing would always be pointed in that direction, and it would be orbiting like this.
That's cool.
Yeah,
doesn't
they're
actually,
actually
like,
always
turn.
tilted,
That's cool how it does that.
like that.
So we
Obviously,
Is it cool,
not to
Jared?
size.
It's pretty cool.
My eyes! Okay, so this is the picture from your lab showing that we are actually at a 23.5 degree tilt. It's not straight up and down, it's tilted 23.5, and these globes are always set for you at that angle. All right.
Please stop talking.
This is a picture of North Star. I just think it's super cool when they take these time delay photography. You can see that somebody put up a picture and they were just focused on the North Star. The North Star looks like it stays fixed as we are rotating around from day to night. The North Star.
It's cool.
All right, so the fixed tilt causes the sun to hit the Earth at different angles during the orbit. And so this kind of tips into part 3. But here's the picture from part 2. And I think it asked you on part 2 in June 22nd when we have the northern and southern hemisphere. So this is north and this is south. Which hemisphere is experiencing summer during June 22nd? The north, because it's getting direct rays of sunlight. The south is getting indirect rays, and so the light has to be spread out over a much larger area, and this is just boom, pointing right at it. So when we're experiencing summer in the northern hemisphere, areas like Australia are experiencing winter. So when they celebrate, if they celebrate Christmas at December, they are actually celebrating Christmas during summertime.
That's weird.
During like,
That's
It's
weird
just
to do.
changed. Yeah, it's different to think that way. Yeah,
can I go to the bathroom?
absolutely.
That'd be weird to have
So here's more information on the fixed tilt. It says this fixed tilt causes the sun to hit the Earth at different angles of light during the orbit around the sun. So because it's tilted like this, right now in the northern hemisphere, we're going to get direct rays here. It's going to be summertime, and the sun's rays are spread out over larger areas, so less energy per square mile. It's going to be winter. This feeds into this part of the lab. And can someone tell me what part of the lab is this? What page?
Oh, that's 3.
Okay, so this is page 3. We did not have you do this section. We did not have you worry about the 15-degree angle. But you were responsible for shining the flashlight directly at it so that it is a right angle. So that means if this was your graph paper and this was your flashlight, then the angle of light was coming down and it was a circle like that you made. And then on this one, we had you go ahead and angle your flashlight at a 45-degree angle, and it spread out that same energy over more space. Yes?
What would happen if there was no tilt to the Earth?
If there was no tilt to the Earth, then then every place on Earth would be experiencing summer at the same time. Every place, and there would be no change of seasons.
That would be weird.
It would just be like if you wanted to, yeah, there would be no change of seasons whatsoever. So if you wanted to go, if you lived in Iowa, you'd have the same temperature all year round. If you wanted to go someplace colder, you would have to fly to the poles and go someplace colder, but you wouldn't have any change of seasons. Your season would be the same thing. Would you like that?
No.
Do you like the changes of the seasons? Yeah, the changes sometimes, yeah. I don't know, I kinda wouldn't mind, yeah. There would be what? It would definitely change our weather patterns, for sure. Yeah, I absolutely agree with you. And you know the other weird thing is that over time, our rotation is slowing down. So our rotation, which means this, not our revolution, but our rotation is slowing. So eventually, like if this is the sun and this is the globe, eventually this thing is going to stop. And we're always going to have one side that is going to be facing the sun and one side that's not going to be facing the sun. So like, where do you think the best place to live would be?
The side was in between.
I would think in between, like on the side, where it's maybe like not quite direct sunlight. I mean, there's gonna be areas that would probably be totally frozen, and there's gonna be areas that are gonna be just like scorched when it starts to, when it stops. Each year, it gets just a few seconds, like minute amounts of time slower. Nothing for us to worry about. Civilizations way in the future have to worry about that stuff. All right. So when we look at this, the big idea here was that you were counting squares. Let's imagine, somebody give me the amount of squares you had in the 90 degrees. Go ahead, Will. 61. Okay, let's say I had 61 squares here. Somebody give me the amount of squares that you had at the 45. Will, why don't you do it so it's consistent? What did you have at the 45? I'm assuming more. You didn't do that one? Okay, so then somebody, what do we have at the more aggressive one? Did anybody do this? Did anybody do this?
I didn't get to count.
Okay, no problem. So let's go ahead and let's imagine that it was 85. So what I want you to do at this part is I want you to write down, if you didn't do it at all, 61 squares for the 90 and then 85 squares for the 45. Yes, dear. As soon as I get somebody who's gone to come back, you go. So we've got 61 and 85 squares. Okay, so now at this portion in the lab, we said that that flashlight is 10,000 units of energy. Everybody get out your phones, please. 10,000 units of energy. We're going to do some math. I asked you to share that 10,000 units of energy across every single square here, and share that 10,000 units of energy across every single square here. So you're going to put in 10,000 in your calculator divided by the number of squares in that circle. So divided by 85, and then somebody else, 10,000 units of energy divided by 61 squares. For which one? What? For 61, how many per square? 463. My bad, I'm so sorry. 163. I'm just going to round up to 163, and that's energy per square. Is that right? Is it 16.3? 10,000 divided by 61? Okay, then 10,000 divided by 85?
117.
What is it?
117.
117 units of energy per square. All right, so here's my question for you. Which area of land is going to be warmer per square? Is this area of land, which we'll label A, or this area of land, which we label B? Which one's going to be warmer per square? Like if you're standing there, you're going to be warmer. Why?
Because it's the same amount, but it's a smaller area.
Yeah, it's the same amount of energy, but over a smaller area. For each square mile, if you will, in this area, you're getting more energy than you are for this square mile. And that's why it's warm. Do you have to use the restroom? As soon as Kendall goes and comes back, then you can go. Who's sitting next to you? Who's, huh?
Galen.
Oh, yes, and they're in the restroom.
No, I think she's skipping.
What?
Going to the restroom.
Because what happens is if I have more than one people go, then it just seems like it's always a nightmare. Nobody ever comes back.
I think,
Caitlin, we're waiting.
oh, she's skipping class. She got caught.
She's sitting on the potty texting. No, I don't know. Are we good here? So then in summertime, listen, in summertime we've got a direct angle. This was the picture of like the little farm. This was if the sun is directly overhead at noon, it's going to be shining down, it's going to be very bright. If the sun only gets this high up at noon, it's going to be like winter or spring or fall. We're going to get much more indirect sunlight, less direct sunlight, so the temperatures are going to be down. All right, let's go ahead and look at the next part of this lab. Seasons. So basically, why do we have the seasons? We experience the seasons because the Earth rotates on its axis that's tilted at 23.5 degrees. This tilt causes the different hemispheres, meaning northern hemisphere and southern hemisphere, to get different angles to the sun at different times of the year. Because of this angle, during winter, the energy from the sun must travel through more atmosphere to reach the poles. Also, a given amount of the sun's energy is spread over a much larger area. So, to wrap it up, different angles of light equals different intensities of light. This equals different temperatures. If there was no tilt, as Jaron asked, there would be no temperature change during the year. We would always have just the same season. It would be like this. Now, would we all be the same temperature? No, but this temperature would never change. This temperature would never change. It would be like fall all the time. I do too. I like that temperature. All right. The mark of our seasons is just talking about solstice and equinox. I just want to briefly go over this because I don't want you to sound stupid when you grow up. Solstice and equinox both mark certain positions in the Earth's orbit around the sun. Solstice is the day that starts either the beginning of summer or winter. Has anybody ever heard of the summer solstice?
Yes, I have.
Equinox means neither hemisphere is tilted towards the sun, and the day length and darkness are equal. So we get 12 hours of day and 12 hours of night. And that's all I want to say about that. Winter solstice, shortest day, summer solstice, longest daylight of the year. Okay, and we're done. I want to show you one video. It's right here. This goes over every part of our, you can't see that. This goes over every part of our lab.
Imagine that you live.
I'm going to get rid of that. Get rid of it? Okay, that's weird. Okay, I don't want that one now. Okay, I want this one. Okay, let me get rid of this. Can I end this? There we go. Go ahead, Kendall, and remember, people are waiting.
There's a big line for that.
There is a big light in the bathroom.
Imagine that you live in North America, and one day you call up your friend in Australia. You guys are talking, and you make plans to go visit him next summer.
So, anytime next summer works for you?
Yep, whenever's best for you. Surprise me.
In a few months, July rolls around, and you hop on a plane for your Australian vacation. Imagine your surprise when you show up at his house, and he tells you,
What are you doing here, mate? It's the middle of winter.
and then you say,
Winter? It's the middle of summer back in America.
and your friend's like,
I don't know what to tell you. July is winter for us.
Okay, I don't get this. How can it be summer in America and winter in Australia at the same time?
that's a great question. I think we can help you out with that. To answer this question, we have to zoom way back and start with a top-down look at the Earth's orbit around the sun. Oh, by the way, everything you see in this video isn't to the correct scale. Now, the Earth's orbit isn't a perfect circle. It's actually an ellipse. You usually see it drawn like this. Lots of people think,
Hey, this must be why we have seasons. When the Earth is close to the sun, we have summer. And when the Earth is far away from the sun, we have winter.
But that's actually not true. If that were true, it would be summer in America and Australia at the same time.
And we know that's not the case.
Exactly. The way we've drawn Earth's orbit here is really exaggerated. People just draw it that way to highlight the extremes. In actuality, there's a relatively small difference between the Earth's closest and furthest points from the sun. If we draw Earth's orbit with the correct shape, it looks like this. You can see it's actually pretty circular, but it's not perfect. So it's not the closeness of the Earth to the sun that causes the seasons. To see what's actually at work, we have to look at the orbit from the side. In our side view, the Earth is revolving around the sun in this orbital plane here. It takes 1 year to go through a full orbit, 365 days. Remember, at the same time, Earth is rotating on its axis once every day. The important thing, for the seasons at least, is that the Earth actually isn't straight up and down. It's tilted at an angle of 23.5 degrees. So, when the Earth is on this side of the sun, the northern hemisphere is angled away from the sun. The southern hemisphere is angled toward the sun. When the Earth is revolving...
Okay, in this position, right here, tell me which hemisphere is going to be experiencing winter.
The northern hemisphere.
The northern hemisphere is actually experiencing winter because it is tipped away from the sun, and so it's going to have indirect sunlight, where the southern hemisphere is going to have the direct sunlight. So actually, it's the northern hemisphere that's experiencing winter.
revolving around the sun, it stays tilted in the same position. The axis doesn't wiggle around or anything. It just stays fixed in a certain direction. So when the Earth is over here, the hemisphere is angled away. When a hemisphere is angled towards the sun's rays hit it directly. That's what's happening in the northern hemisphere here. But when a hemisphere is angled away from the sun, like the southern hemisphere here, the sun's rays hit it indirectly.
Okay, so what difference does direct or indirect sunlight make?
Oh, there's a huge difference. Let's take a look with a simple experiment. In this experiment, we're going to use a flashlight to simulate the sun.
See, nobody likes
Say
that.
that the flashlight is a particular sunbeam. If it's shining directly, all its energy is concentrated in a certain area.
Just like we did.
But if the sunbeam is shining indirectly, the area is larger. This means that the same amount of energy is spread out over a larger area. So, in a particular point on the paper, it feels colder in the indirect sunbeam than in the direct sunbeam. And the more indirect the sunbeam, the larger the area. It's important to note that the amount of energy in the sunbeam is always the same. It's not changing. However, if it's spread out over a larger area, we feel it less. Let's take a look at what this means for the Earth. Here we have a globe that's angled at about 23.5 degrees. It's June, so the northern hemisphere is angled towards the sun. If we shine the flashlight directly on the northern hemisphere, we see it illuminates a certain area. But when we move the flashlight to shine indirectly on the southern hemisphere, we see that it's illuminating a larger area, just like we talked about. So let's put it all together. When the northern hemisphere is tilted towards the sun, it's receiving direct sunlight. It feels warmer, which means it's summer there. And the southern hemisphere is receiving indirect sunlight, which means it feels cooler. That's winter. 6 months later, when the Earth is on the other side of the sun, we have the opposite. It's the southern hemisphere receiving direct sunlight, so it's summer there. And the northern hemisphere is receiving indirect sunlight, so they're having winter. And now you know the reason for the season.
Awesome. So it's not how close the Earth is to the sun that matters, but instead it's the tilt of the Earth.
Which is also why it's winter in Australia at the same time as it's summer in America.
You got it.
Well, I think this is the most educational vacation I've ever had.
And there's so much more to talk about. Did you know that the Earth...
You know, I actually think I'm good for now.
Oh, okay.
So, what'd you like to do?
All right, so do me a favor and go to the very last page of your lab. Let's go to the very last page of our lab. It looks like this. Now what I want you to do is wrap it all together. 4 friends were talking and they all had different ideas about why is it warmer in the summer than the winter. So now Natalie says it's because the Earth orbits closer to the sun in the summer than the winter. If you agree with her, put her down here. Van, it's because the Earth's tilt changes the angle of the sunlight hitting the Earth. Tessa, it's because winter clouds block the heat from the sun. Miguel, the earth tips back and forth on its axis, tips towards the sun in the summer and away in the winter. From this lab, from what we talked about, from the daily question, I want you to write down an explanation for which friend you agree with. You're synthesizing your information. Write down who you agree with and explain the reasons for the seasons. Explain the reasons for the seasons. Just in case, you know, you have to do it on the exam. You didn't do anything. But I was going over, right here. Which one do you agree with, and then explain why. Put this away, otherwise I'm taking it. You're the worst. If your phones are on your table, if you would please put them away. We don't need them right now. I'm going to go ahead and use my brand new little hourglass.
That's cool.
Thank you. How are you doing on time?
Pretty good.
You're a really good on time.
14,
Yep.
17.
Yep. So what I'm going to do while you're doing that is I'm going to be passing out the lab that we are going to start today. It is a 2-part lab. For those of you that have a packet of information from Mrs. McGrain, I gave you this in your packet, so you don't need to take another one. But if you can take one of these, please, and pass it down. I know I've given you too many. Could you take one of these and pass it down, please? Take one of these and pass it down. We're going to be starting this lab in class today. So we talked about the factors that explain an area's climate, its temperature, and its precipitation. Karen, could you take that and pass it down? We talked about how the different factors that affect an area's climate and different factors that affect an area's precipitation. We talked about how climate can change over small periods of time with small shifts, and that's seasons. And now we're going to start looking at how climate can change over long periods of time. And in order to know that that happens, we have to study what's called paleoclimates. What do you think paleoclimates are?
Ooh, I don't know.
Yuma.
The history of
Yeah, like ancient climates. Like if you're a paleontologist, you study ancient animals, right? You're studying ancient things. In this case, we're studying paleoclimates. So you can be a paleoclimatologist, and then that means you're studying past climates. In order to study a past climate, to know that it was different than our present climate, we have to find data or evidence that we call proxies to show that the climate has changed. So we have to find something that was around back then that we can discover and say, oh, look, the climate was different because of this evidence. In this lab, we're going to look at pollen grains. How many of you know what a pollen grain is?
Is it like from the flowers?
It is. What is it from the flowers?
Something a bee collects.
Yeah, it's basically, it's flower sperm. So pollen is the sperm of flowers and plants. And what it does is, at certain times of the year, it lets off lots of its pollen in the hopes that it will be carried by animals, by birds, by bees, to other plants, and then it will fertilize those other plants. Me, myself, I'm allergic to it, right? So plant sperm can't handle it. In this investigation, you're going to analyze sediment samples. Sediment samples means I've got dirt in bags for you. So you've got a sediment sample right here. And this was collected in Colorado. Hint, hint. I'm just playing with you, but we're going to pretend that this was all sediment collected in Colorado. We're going to then use that to determine the amount of pollen in the samples. Now the pollen, because pollen is very small, it's microscopic, you can't see it with your eye, I have taken different colored paper hole punches, and that's going to simulate the different kinds of pollen. So it's large enough where we can see it. So we're going to determine the type of vegetation, meaning plants, alive during that time period from that pollen. This will enable you to infer or guess about the likely climate at the time that the pollen was shed. because only certain plants can survive in different kinds of climates. And remember, for climate, we're looking at precipitation and temperature. So you're looking at, is it a dry or wet climate, or you're looking at, is it hot or cool? Okay, that's what we're looking at. The following exercise was actually taken from pollen data that I collected from a peat bog in the Colorado Rocky Mountains. Okay, so this is like legit changes in climate that we're going to be tracking. So procedure, number 1, examine your sediment sample. Each sample contains pollen from plants that grew in the area at the time the sediment was deposited. Empty the sediment into the pie pan. I don't have pie pans, I've got paper plates. So every group is going to have a paper plate. Dump your bag basically in the paper plate. Sift and dig until you found all the pollen grains. Separate the pollen from the sediment. Separate the pollen grains by color. So you're going to go ahead and look at a key that I have given you on each table, and I will show you what it looks like. It's this. It says climate pollen, basically. So it's got plant species, and then over here on the side, if you find a yellow circle, it's a ponderosa pine, and it tells you how ponderosa pines like to live. Ponderosa pines are long-needled pines. They occupy warm, dry slopes. So then maybe that's a clue to say during the time period that these ponderosa pines were living, maybe it was a dry, warm climate. But one plant is not enough. We want to see other examples of pollen in that layer that corroborate that it was dry, warm climate. Do you understand what we're doing? Okay, so that's going to be what we're doing. You're going to use the pollen key, which I just showed you, to determine what species of plants are represented in your sample, and then we're going to calculate the percentage of the total pollen. We'll probably be able to get to that at the end. Turn your page, please, so that you can see what the data collection table is like. We have got these different sediment layers. They are not in this layer, right? We mixed up the layers. I had some graduate student help me collect them. We had them all nicely organized, and then they all dropped and got all mixed up. So we have to go ahead and work together to figure out the correct layers that they go in and how the climate changed. If you see that there was a ponderosa pine, and let's say you have baggy D. In ponderosa pine for baggy D, you'd say 1 check mark. And let's say you found 2 more of those. That's how many ponderosa pine you found there. If you found Engelmann spruce and you found 2 of them, you would do that. If you found 5 limber pine, you would do that. That's basically what we're doing. Don't just tell me, yep, limber pine is in there. Tell me how many. Because maybe we'll determine that it's transitioning from a wet, moist, cool environment to more of a dry, warm environment based on the pollen that we're seeing. Sound good?
Yep.
All right, so what we're going to do is I'm going to put you in groups of 6 because I have 6 bags. Please make sure that you are looking at what bag your group belongs to. We have enough time to collect our data, and then we'll come back together. We can do percentages together, and then tomorrow we'll share data and finish the lab. All right, so this group plus, ooh, it's a big class. 1, 2, 3, 4, 5. I'm going to have U4 plus U2. Could you please go to table 7? I'm going to have U4 plus U2. Could you please go to table 6? I'm going to have U4. Could you please go to table 5? I'm going to have U5 in the back. Could you please go to table 4? Then I'm going to have U4 go to table 3 and U4 go to table 2. And I don't have any bags at table 1. All right, Dobbins, look at what bag you have and circle that on your data table. Look at the bag that you have, and if you've got F, circle F so that you don't get lost. Dump it out and start counting. Oh, thank you, honey. I appreciate that. Dump them out and start sifting through. What did I do with that? It's just dirt. It's just like playground sand and purple sand. I just made it all different so that it looks different. Okay, sweet.
Yeah. Are we
Can somebody at Alex's table help them figure that out? Take your plate, open this up, and dump it on the plate, and then we're going to try to figure out, you're going to look for those little colors, okay? You're going to look for the little colors. Here's your key right here. Okay, you guys can have one and you have one. So take this out and dump it out and sift through it. So we're looking for little tiny punches of color. It's just dirt. Like seriously, it is dirt is not
Can I
gonna
take
hurt
them
you.
out?
Yes, yeah, take them out. The only thing you have to do is make sure that they all go back in. Lime green is going to be different than the dark green. Dark green is more like your Kelly green. Lime green is kind of like your, well, light green, like the color of my iPad cover. Okay, don't lose energy. This is like a light green, not a dark green.
Hey guys, so
Good? Can you put it more in the middle so everybody can see it? Sort through. Ooh, nice sorting. That is definitely the dark green, not the light green color, okay? And then people at home, what you're doing is you are then just filling out your data table. In order to do our percents, if you have something like this where you have 5 here, 4 here, and 3 there, and that makes it, you add up and you have a total of 12. Then to figure out your percent, you take 3 divided by 12, and that would give you your percent for how much of the sample is your percent of sedges and mosses. And then you would do the same thing for 4, and you'd say 4 divided by the total, which is 12, and you'd figure out what the total would be there for your percent, and you'd put that right there.